hope you are all well and healthy and ready to learn the new things. So my name is Palak Patel. I am working in the Mahatma Gandhi Institute of Technical Education and Research Center, Navsari, in Civil Engineering Department. I am going to teach you the subject is design of reinforced concrete structure. In this subject, we are going to learn design of water tank. So in this video lecture, we will cover on the ground water tank design as well as underground water tank design. In the previous lecture, we covered rectangular water tank and circular water tank for the on the ground water tank design and rectangular water tank for the underground water tank design. And in this lecture, we are going to learn circular water tank design. So shall we start? Underground circular water tank. We have a circular water tank underground. We have two. One is sliding base and second is rigid base. And two conditions: tank is empty and tank is full. Tank is empty and tank is full. So in this lecture, we are going to learn sliding base water tank, and for these two conditions. Okay, so you can see this design a circular water tank with a flexible base capacity 5 lakh liter below ground level. Use M30 grade of concrete and Fe415 grade of steel. This example asked in winter 2030 as well as summer 2016. So we have the first of all we have to find out dimension of the water tank. Okay, we have a capacity 5 lakh liters. So we provide a depth of water tank 4 meter and 0.2 meter free weight. So depth of water is 3.8 meter. These are the trial and error method. What we are doing, we are just assuming. Okay, height is 4 meter. So by height we can calculate the diameter. So pi by 4 d square. So is 500 mm square. So provided diameter is 13 meter. Provided diameter is 13 meter. After this calculus, after solve this example equation, we can find out diameter 100 meter. First step 1, when tank is full and tank is full of water and no soil pressure outside. No soil pressure outside. At a time, maximum pressure at the base is 14 kN per meter square. Is 14 kN per meter square. So for the circular, we have to calculate maximum hook tension. So T is equal to PA into D by T. So 40 into 30 into 12. So 260 kN per meter square length. Now one more condition here. Why we calculate hoop tension here? Why we are calculate hoop tension here? First, with flexible base. With flexible base. And what happened when we calculate for the flexible base? Here. Circular tank with a flexible base. Let's change a paint color. The side wall free to expand contrast at the joint between the floor and side wall is flexible. And when tank is full of water, no soil pressure outside. First condition. Condition 1. Condition 1. The full of water, no soil pressure outside. So maximum pressure at base, PA is equal to gamma W into capital H. PA is equal to gamma W into capital H. So hook tension at a base is equal to capital T. Capital T is equal to PA D by 2 per meter length. PA D by 2 per meter length. And for the condition 2, when tank is empty, the saturated soil pressure outside. At a time, maximum pressure at a base, PA is equal to Ka gamma dash into capital H or plus gamma W into capital H. So hoop compression force is equal to PA D by 2. Here is a tension and here is a compression. Okay. So here is the two condition here, but the pressure will be changed. The pressure is changing. Now we are going to calculate hoop tension is equal to P tension. PA is equal to D by 2. So 40 into 30. So 260 kN per meter square. 260 kN per meter square. Okay. Sigma ST from the IS 3370 part 2 2019 table number 4. I explain how to calculate sigma ST. So area of steel required T divided by sigma ST. So 200 mm square for the two faces. Area of steel required. So provided AST for the one faces is 1000 mm square. So provided 60 mm dia at 200 mm center to center on each face in circumferential direction. So let T will be thickness of the wall in mm. We are going to calculate thickness of the wall. We are going to calculate thickness of the wall. How we calculate thickness? We can calculate thickness from the IS 2000 page number 80, and we can find out tensile TC T divided by AG upon M minus 1 into AST. T divided by AG upon M minus 1 AST. So we can calculate M from table number 3.4. Sigma ST we have 1.5. M is equal to 280 divided by 3 sigma CBC. So 280. So value of M. Okay students, so you can see here is we can calculate M, then after sigma CBC, then after we can calculate this, wait a minute, just change a pen color, right? So 1.5, 2. T we calculated, AG and AST. What is AG and AST? First of all we have to calculate AG. First of all, we have to calculate AG. AG means area of gross. Area of gross means 1 meter and T is thickness. 1000 into T thickness is the area of gross. And same way we have the AST means area of steel. Area of steel. So by these two value we can find out thickness, which is 200 mm. So we have a thickness T is 200 mm. Now our design is completed for the condition 1. Now step 2. For the condition 2, when tank is empty, outside soil pressure. So we have calculate K is 1 minus sin phi, 1 plus sin phi. So it's 1/3. Gamma dash we have, and 10 is water pressure. So gamma dash is equal to 7. PA is equal to Ka gamma dash H plus gamma W into capital H. So by this pressure we have 49.33 kilonewton per meter square. So by this pressure we can calculate compression force. We can calculate compression force. So compression force is PA into T by 2. So 49.33. So it's 3320.45 kilonewton per meter length. Here is a maximum compressive force. So we can calculate sigma CC from the IS 3370 part 2 2019 table number 2. From this we can find out CBD is 1.6 is less than 8. So our design is safe. Our design is safe. So we can provide vertical reinforcement. Here which design we talking about? We talking about regular reinforcement. Here we talk about thickness. We are talking about thickness of the wall. By this sigma CC you can clarify, you can check thickness of the wall. Sigma T is okay, right? Now we are going to calculate vertical reinforcement. How we calculate vertical reinforcement? Calculate by provide minimum reinforcement. D is equal to 200 mm. So capital D is equal to 100 mm. P minimum is 24. P minimum is 0.24%. So for the one zone, we have AST is wait a second. AST is equal to 0.24. Here 240 mm square for the one face. So we provide 8 mm dia at 200 mm center to center on the both face in a vertical direction. Okay. That why we have provided main reinforcement at a different depth. we provide a main reinforcement at a different depth. Different depth means at 3 meter from the top. We have just calculated a height 3 meter. So tension will be changed here. Hoop tension will be changed 195 kilonewton. So by this hoop tension we have equation T divided by sigma st. So we calculate provide 60 mm dia at 260 mm center to center on a both face in a circumferential direction. Then after we have provide 2 meter length. So height is 2 meter. So AST is 1000. So AST. So tension will be changed. So the same equation we have the AST will be changed. So provide 12 mm dia at 220 mm center to center on a both face in the same reinforcement provided in the remaining portion. Now we are going to calculate step 3, design of base. Design of base. So we have going to design a 4 meter head of water providing 150 mm thick base. For the 4 meter head of water we provide a thickness of base is 150 mm. Thickness of base is 150 mm. So provide equal requirement 0.24 percentage. So AST 0.24 divided by 100. 1000 means 1 meter and 75 mm thickness. 75 mm thickness. So 180 mm square. Why this is 75? Why this is 75? Assume provides calculated reinforcement in one face. One face near the possible of upper surface. So 150 is the total thickness, but we have to design for the upper face only. So it's 75 mm. So provide 8 mm dia at 270 mm center to center on a both way at top. So our design is completed. You can see here. For 1 meter, here is a 12 mm dia, 200 mm center to center, 60 mm dia, 260 mm, 8 mm dia, 280 mm, 60 mm dia, 200 mm center to center. Stiff painting and joint sealing compound and 8 mm dia at 270 mm center to center at base. Look at here. Reinforcement at the upper force. Lower force is a PCC. Lower portion is a PCC. So our design is completed here. Okay students, here our example is completed. Circular water tank with underground with flexible base. So in the next lecture we will cover circular water tank underground with rigid base. Okay. Till then, goodbye.